And as he's doing that, just so there's verbal communication about the fact that this entire meeting will be recorded and it will be transcribed as well. It will be uploaded onto YouTube with a private link, so you can only watch it if you have that link. It's not public facing, but you can circulate that link anywhere that you'd like to. And Riccardo, we can always send it to you if you'd like it as well, if you'd like a record of the presentation as well as the discussion and Carl's feedback towards the end. Yeah?
Okay. Okay, thank you.
Yep.
So
yeah, I'm just gonna give it like one more minute and then we can start. Yeah.
okay.
Do you have a question?
Sorry?
Do you have a question?
Well,
No?
no. I think that
Okay.
when all of you are ready, I can start with my presentation.
Okay, wait. Yeah, I just wanted to make sure everyone's in first. Okay, wonderful. So I'll just give a brief overview as to what the structure of the meeting will be like, and then I'll hand it over to you to introduce yourself and the presentation itself. Yeah. So we'll have around 40 minutes of you talking and giving a presentation, and then we'll have 20 to 30 minutes of an open floor discussion with all of the attendees, so we can have some Q&As or a discussion regarding any specific questions that you may have that you want feedback on. So if you have, like, for example, a interpretation of some results and you're not sure about how to do that, then you can ask that to the attendees themselves. And then we'll wrap it up with Carl providing a summary as well as some feedback towards the end. And we'll have around 20 to 30 minutes of that. Yeah, but yeah, just a reminder to everybody that this entire meeting is recorded. So if you want a copy of the presentation and the recording, then please let us know via the email. Wonderful. Okay. Thank you, Riccardo. Off to you.
Okay, thank you. Can you see the screen?
Yep, we can.
Okay. So, welcome everybody. My name is Riccardo Marramotti. I'm from the University of Modena and Reggio Emilia in Italy. And I'm going to present a project about an active inference model for a motivational Stroop task. Most of the analyses that I will present were performed during my period of research in Oxford. Last summer, I went for 3 months in Oxford as an academic visitor, and I had the possibility to meet Thomas Parr, who helped me a lot for this work. So this is the outline for my presentation. First of all, I will introduce the motivational Stroop experiment, and then I will present the real behavioral data of our participants. Then I'm going to present the generative model, and finally the model inversion with the parameter estimations. So first of all, the Stroop experiment is a psychological test designed to measure the ability to suppress automatic responses. In the Stroop experiment, participants are shown words that are name of colors, and they had to indicate the color of the written words. So if you look at the words in the left panel, it should be easy to do this task, while if you look at the words in the right panel, this task should be more difficult. This is because in the left panel, trials are congruent. So for example, red is written in red. In the right panel, trials are incongruent. The Stroop effect consists in lower accuracy and slower reaction times in the incongruent condition. And this is caused by the fact that our brain reads words in an automatic way. So identifying colors is an action that requires effort. So we build a modified version of the Stroop task, and we gave it to 20 healthy young subjects. Our experiment was divided in 4 sessions, and each session was divided in 2 blocks. In one of them, the target was the color of the word, while in the other block, the target was the word itself. I said modified version of the Stroop experiment because we added a manipulation on the motivation involved in the task. So in 2 out of the 4 sessions, the participants had to respond with maximum effort. In the other 2 sessions, they had to be as relaxed as possible. So considering that trials can be congruent or incongruent, we have a 2 times 2 times 2 factorial design with 3 factors: congruence, target, and effort. This slide shows the real behavioral data for our dataset. So the first column refers to the average accuracy, and the other 2 columns refers to the distribution of reaction times. As you can see, the color incongruent condition was the one with the lowest accuracy and the highest reaction times. The word incongruent condition was a bit more faster and more accurate, but the congruent conditions had the best performance. If we compare relax and exert, we can see that in the relax condition, participants were overall slower. So I think that with this figure, we can see that the Stroop effect is here in the data, and we have also a difference between the relax and the exert condition. So the aim of the study. The idea behind this experiment is that in everyday life, in some occasion, we are told to be relaxed. In other occasion, we are told to be to use as much effort as possible. So with this experiment, we want to study the effect of instructions on motivation while performing a task. So effort is a key point for the study, and effort can be defined as the divergence between the required behavior given the context and the usual behavior. This definition comes from a recent paper of Thomas, Carl, and colleagues, in which they build a theoretical active inference model for the Stroop experiment. So they build the theoretical model, and they used the simulated data for the model. Now we are trying to adapt the model for real data. But crucially, we don't want only to see the effect of effort. We want to see what happens when we tell the participant how much effort to use. And for that reason, our aim is not only to predict responses. We want to estimate 2 parameters for each subject: the motivation C and the bias E. The motivation C represents the preference for being as fast and as correct as possible, while the bias E represents the habit of responding to text rather than color. So, for example, when E is high, it means that it's very difficult for the participant to suppress the automatic response. So we built a model that needs to recreate the shape of the data, but most importantly, we wanted to answer these 2 questions. Does voluntary modulation of effort affect the motivation? Does the voluntary modulation of effort affect the bias? Before moving on to the generative model, it's important to say something about the reaction time distribution. We assume that reaction times were distributed based upon confidence. So as you can see in the formula, we have an entropy H. H is the term based upon confidence. So H is always higher than 0, and H approaches 0 when the participant is almost certain about his choice. So it's a confidence about the choice in the task. We have also alpha. Exponential of alpha approximates the median reaction time in the fastest condition. So alpha tells us how fast the participant can be. And we have also n, a random variable with zero mean and exponential of v variance. So v is associated to the variance of reaction times. The question is, why do we need this formula? Well, the estimates of C and E are affected by how fast is the subject on average. And we don't want to model how the participants are fast. We want to model the differences across conditions. So we need to find proper values for alpha and V in order to fix them in the main model. To do so, we defined a reaction time model with 8 equations. As you can see, I goes from 1 to 8. 8 equations because we had an equation for each condition. We are in a 2 times 2 times 2 factorial design, so we have 8 conditions. In the formula, n is the same random variable we've seen in the last slide. Ri represents the reaction time in the condition I, while we are optimizing on the parameters Zi and V. After that, we can define alpha as the minimum value of Zi, and in this way, alpha represents the median reaction time in the fastest condition. So, in this way, we defined values for alpha and V. Alpha and V are not condition dependent, so they will be considered as fixed parameters in the main model. Just a slide to show the result of this reaction time model. In the slide, the blue color represent congruent trials, while the red color represent incongruent trials. And in solid lines, you can see the distribution estimated by the model, while the histogram represent the actual data. This data refers to a specific subject that I choose randomly from our dataset. I think that visually the fitting seems quite nice, and we can see also that this participant in the relaxed condition is overall slower compared to the exert condition. So now we can move on to the generative model. As I said before, we used active inference. In active inference, each subject has a generative model that predicts how sensory data are generated. So in active inference, action and perception are combined, and actions are taken in order to minimize the surprise. The surprise represents how much the outcome differs from the habit. So behavior is the result of updating prior beliefs in the generative model with the aim of minimizing surprise. Crucially, differences among people can be seen as differences in prior beliefs. So in our case, differences among people will be seen as differences in C and E. This slide shows the structure of our generative model. As you can see, is a two-level model, a two-level Markov decision process. We have a slow level in which each time point corresponds to a trial. We have a fast level in which each trial is decomposed on each subcomponents. And the slow level influences the fast level, and then the fast level influences the outcome. We have also parameter lambda. Lambda is a temperature parameter that quantifies the variability present in the data. So when lambda is low, we have higher variability. And as it is a generative model, we can choose some values of C, E, and lambda and simulate data for the action U. In this way, we can also simulate data for the choice and also for the reaction time. And as you can see, the reaction time is influenced also by alpha and V we estimated before. Another thing that we need to notice is the presence of the policy pi at the slow level. So the policy does not influence directly the outcomes. because the slow level influences the fast level, and then the fast level influences the outcomes. An important thing to consider when building a model of behavior is the fact that the model should reproduce characteristics present in the real data. In our case, the model should be able to reproduce the speed accuracy trade-off. In the slide, you can see on the left the accuracy and on the right the reaction time for some values of C and E. If we look at the leftmost column in both figures, we are fixing C at a very low value. Looking at the two leftmost column, when E becomes higher, we have we have lower reaction times, but also lower accuracy. At the meantime, if we look at the rightmost column, when E becomes higher, we have better performance and better reaction time. So I think that this slide shows us that the model is capable to reproduce all the possibility of speed accuracy trade-off. The fact that some people, when they try to be as fast as possible, they commit more errors. So we can move to the model inversion. Remember the aim of the study. We want to answer these two questions. Does voluntary modulation of effort affect the motivation C? Does voluntary modulation of effort affect the bias E? Before inverting the model, we need to find prior values for C, E, and lambda. I'm not going into the details about how I choose these values, but I want to give you an idea. So as the prior preference C, the hypothesis is that being correct is about 7.4 times more probable than being incorrect. As for the prior bias E, the hypothesis is that our brain expects to read the word about 65% of the time. And finally, as for the prior variability lambda, we choose a value that we found in the literature. For all these parameters, the prior variance was 1/4. That is a quite high value. In other words, we are allowing the parameters to go away from the prior, and our approach is highly data-driven. Mathematically, this model inversion consists in a minimization of a functional, and in our case, the functional is the log likelihood, composed by two parts, one for the choice data and one for the response times. So as the generative model can produce data both for choices and reaction times, we are using both of these informations for the parameter estimation. We estimated the parameters separately for the relax and the exert condition, and in this slide you can see the result for a particular subject of our dataset. Is the same subject we've seen before for the reaction time model. In the first column, you can see the parameter estimate, and as you can see, C is higher in the exert condition compared to the relax one, while we don't see such a large difference in the parameter E. After the parameter estimation, we tried to generate data using the parameter estimated by the model, and then we compared the real data with the simulated data. So, for example, in the second column, you can see the accuracy simulated by the model in orange, while the blue dots represent the real accuracy of this subject. I think that it's clear that the model understands that the color incongruent condition is the one with the lowest accuracy, but we have also to admit that our models tend to commit less error compared to the subject. If we look at the third and the fourth column, we have a comparison also for the reaction time. The blue lines represent the model simulations, while the red lines represent the distribution in the data. Solid line represent the congruent condition, and the dotted line the incongruent one. So as for the fitting purposes, we need that the two solid lines should be as near as possible, and the two dotted lines should be as near as possible. Also, in this case, the model understands the differences between conditions, but at the same time, we don't have a perfect fitting in each condition. So the question is that lack of fitting a problem? Well, I think that we are using a small amount of parameter, so it's impossible to pretend to have a perfect fitting in all conditions and for all subjects. And another thing that we need to consider is that we are not trying to reproduce the data. We are trying to simulate good values for C and E. So I think that even if we don't have a perfect fitting, these results are sufficient to pass at the group level analysis. So moving on to the group level analysis, in this slide you can see the estimates of C and D for all the 20 subjects. As you can see, C is consistently higher in the exert condition, while E shows more variability. For example, if you look at the subject 10, we have a similar value for E in the relax and in the exert condition, while in subject 12 we have a very high value in the relax condition and the value near 0 in the exert 1. So this gives us a visual assessment, but we can also be more specific with a real group level analysis. And we perform group level analysis using parametric empirical base. In parametric empirical base, you need to define a design matrix that takes into account the causes of variability across subjects. In our case, the effect of interest was the effect of the exert condition on C and E. We had 20 subjects. For each subject, we trained 2 models. So in total, we had 40 models. So in the design matrix, the first column represents the effect of interest, that in our case is the effect of the exert condition on C and D. So in our case, we have in the first column a value of 1 for all the rows corresponding to the exert models. We will have 0 for all the rows corresponding to the relax models. All the other columns of the design matrix represent the subject variability. So we will have a column for each subject. And for example, in the second column of the design matrix, we will have 1 in the 2 rows corresponding to the first subject. To test the significance of these parameters, we use the Bayesian model reduction. In Bayesian model reduction, you need to define a model space. In our case, the model space is composed by 4 models. One which with both C and D switched on, a model with both C and D switched off, and 2 models with only one of them switched on. Then a model posterior for each model is estimated, and we can obtain the estimation for the parameters as a weighted average. I said weighted because we are weighting on the model posterior. So in our case, as you can see in the slide, the 4th model, the one with both C and D switched on, is the one with the highest model posterior. But also the 3rd model, the one with only C switched on, has a non-zero posterior probability. So as a consequence, only C has a posterior probability higher than 90%, and only C increases significantly in the exert condition. So we can conclude with the main result of our study, that is the fact that the main feature of voluntary modulation of effort is to feel more motivated, is an increase in motivation. So as I'm approaching the end of the talk, I will recap the main messages. We are using a motivational Stroop experiment, and in Stroop task, reading colors requires an effortful inhibition because we have to suppress an automatic response. We are using active inference to model this task, and in active inference, differences among people can be seen as differences in prior beliefs of the generative model. Then we inverted the model, we applied parametric empirical base for the group analysis, and we obtained that the main feature of voluntary modulation of effort is to increase the motivation. While on the other side, the impact of effort on the habit of reading words is something that vary across participants. This study has also future directions. So first of all, one thing that we can do is to repeat the task on patients with states like fatigue or burnout, and see if these states can influence how the participant perform the task. Another thing that we want to do is to adapt this method to other famous psychological paradigms. For example, we would like to adapt this method for emotional Stroop. In Modena, we are collecting data on patient on the emotional Stroop. The emotional Stroop is a variant of the Stroop task in which the participant is shown words that are not name of colors, but words can be or not related to their own disease. So with this slide, I'm concluding my presentation, and I want to thank you for your attention.
Wonderful. Thank you so much. Can we please have everybody unmute and just give him a round of applause? Maybe even turn on your cameras if you can. Just to give him a round of applause. Thank you so much, Riccardo. Thank you. Are the claps not picked up by microphones sometimes? Because I think it like does the noise cancellation and then it gets rid of the applauses. But anyway, yes, thank you. This was a very, very neat experiment and very neat study, and you explained it very, very clearly and very well. I was able to follow it in a very relaxed manner, let's say. I didn't require too much effort. So let's open the floor for any questions, any discussion items, and also Riccardo, if you have any specific questions as well, feel free to ask. I did see a raised hand before, but I couldn't get the name, so yeah. Does anyone have any questions? No? Okay. I do have a question regarding the methodology. So with regards to the experiment, how did you manipulate whether someone was in a relaxed state or whether they were putting in a lot of effort? Because the congruent and incongruent conditions of the Stroop task already does that to a certain extent. And from what I understood, you added another layer of motivation that you were, yeah. So how did you implement that?
Well, in the experiment, we tried all the possible combinations of congruence, target, and effort. So in 2 sessions, they had to be relaxed, but in this session, they saw both congruent and incongruent trials. And in the other 2 sessions, the participants had to be to use as much effort as possible, but they saw congruent and incongruent trials. And well, I think that we can see something also in the behavioral data, because as you can see here in the accuracy, in the relaxed condition, the accuracy of the coloring congruent condition is a bit lower compared to the relaxed one. So if we compare relax and exert, we have quite the same accuracy in the congruent condition and the higher accuracy in the coloring congruent condition. So yes, it seems that we have also a bit of difference between the relax and the exert condition on how the participant dealt with the congruence of the stimuli.
Yes. So this was a within subjects, like all same 20 people were in the relaxed state and were in the exert effort
Yes.
state, right? And they did this on separate days, you said?
Well, they did it in the same session, and some of them started with the relaxed block, some of them started with the exert, and it was balanced.
So how did you implement this within the experiment for the participants? For example, did you say with the instruction, you have to complete this block in the most relaxed state? And then like, I don't know, did they have relaxing music in the background or something like that? Or was it just purely instructional?
Just per instructional, because what we wanted to see is the effect of verbal instruction on performing the task. The only thing that differed between the two conditions was the instruction.
Yeah. Okay. That makes sense. And so was it, like it's clear that it's reflected within the data, this manipulation that you did with the color incongruent ones, right? And that's the one that you just gave me an example for. But were there any significant differences with the other three within the 2x2 matrix? Or was it just color incongruency condition that there was a difference between relaxed and exert motivation?
Well, in the behavioral real data, the only one with a significant difference was the coloring congruent one.
Okay.
But this was only the starting point for our analysis, because the main topic of our analysis was to find an estimate of the parameter for the motivation and the bias for each subject and for each of the two conditions.
Okay,
So,
wonderful. Thank you so much. Does anyone else have any questions? If not, I have another one, but okay. I'm gonna ask my second question. Okay, actually there are two questions, if that's okay. The first one is in one of your slides, I think you took this out of the Thomas Parr paper, for effort being described as the difference between required behavior within the context and the usual behavior. So was that implemented within the generative model, or like were you able to do some comparison in that way? And how would you define usual baseline behavior versus contextual behavior?
okay. So in that paper, there was a mathematical definition of effort with a formula that included also the parameter that I included in the model, because it was that paper was for an active inference model for the Stroop task. So it was a theoretical one, but was also the starting point for our model. So we could adapt the definition of effort also for our experiment, but I didn't do it. But I'm sure that we could do it with a bit of mathematical work.
Yeah. Okay, awesome. And the final question I have is when you were presenting the slide on the priors for the parameters that you had before you conducted the model fitting, you
Yes.
had mentioned that you weren't going to go into the details, but now I'm actually interested in the details as to how you got to those prior values for CE and lambda.
Okay. I have also some slides about it here. So we wanted to find values sensible according to our data. So another time I took the paper of Thomas Parr and colleague, and I saw how simulated data of their work. Well, I saw the simulated data of their work. So I defined this quotient Q, and I calculated it in our data. I calculate this quotient also for my data, and with a proportion, I founded a value for the prior. So it's like an heuristic that I used for finding the values of the prior. But at the meantime, I used a high value for the prior variance. So I was allowing the parameters to go away from the prior. And I saw in our result that for a lot of subjects, the actual parameter were very far from the prior. So I think that this choice was more like a starting point to avoid the problem of local maximum that you can have when you do every optimization problem. And yeah, so this is for ENC,
So,
while for lambda I use a value that was used also for in the paper of Thomas Parr and colleagues.
okay. And so did you conduct some sensitivity analyses in order to make sure that you didn't fall into the local maxima or minima? So just having completely different priors for each run and then having the same results?
Well, the prior is the same for each subject and for each condition. I use the same prior for each subject and the
Yeah.
same prior for relax and exert. The only thing that I did is to use a different prior from the one that was used in the paper of Thomas Parr and colleague.
Yeah. No,
I did the sensitivity analysis looking at the fact that the free energy for each subject had a growth because when the free energy stops to grow after the first iteration, it means that there is a problem. In my case,
yeah.
for each subject, I had a sensible growth in the free energy,
Mm-hmm.
and I thought that for that reason, I didn't have the problem of local maxima.
Okay. Okay. Yeah, that makes sense. It's just when I did like a model fitting paradigm with some behavioral data as well, uh, what I had done was even though I chose some priors for the parameters for sensitivity analysis, I also conducted, I think, like 3 or 4 other iterations of the model fitting process, but added different priors. So not different priors for each participant, but a different prior for all of the participants to begin with. So for example, over here, if you're using 0.265, for another model fitting procedure, I would use like 0.6 just to make sure like within the bounds. Yeah, but that could just be like another way of doing a sensitivity analysis if you needed to. But yeah, are there any other questions from anybody and also from you, Riccardo, if you have any questions for anyone here specifically? Otherwise, I will. Yep, okay. I'll just hand it over to Carl now. So, Carl, it's your turn.
Thank you. Is it my turn now?
It is. Yeah.
Excellent. Good. We have a Thomas online. Which Thomas is this?
Oh, Thomas, we can only hear some white noise. We can't actually hear you.
Is that any better?
That is. It
Hello.
sounds like par.
It
That's
does sound like a Thomas Parr, doesn't it? Perhaps we
Yeah.
should ask Thomas
Hey.
to do the first 10 minutes of feedback.
Well, so I've discussed a lot of this at length with Riccardo already, so I'm curious to hear everybody else's feedback, to be honest. I was very impressed with the work that he's done, and I thought very sort of clearly articulated question, nice clean design. I really like the sort of simplicity of the exertion, relaxation, manipulation as a sort of first step in terms of thinking about what experimental effects we can look at using this sort of task. So yes, I've been very impressed by what he's done, and I'm curious to hear how everybody else reacts to it. I thought interesting question really about the sensitivity analysis and whether it's worth, because I can imagine that being something that reviewers might ask for. I think the prior, I can't remember now what the prior variances were, but I think they were sufficiently relaxed that it should stand up to that. Obviously, one of the benefits of doing a sort of variational Laplace approach to fitting it is that anything with a or the free energy minima that it finds are necessarily those with a relatively low curvature or relatively low second derivative in the free energy, which means that moving the parameters around a little bit shouldn't cause much change in terms of the overall results. But it is also a relatively nonlinear model, so there certainly are points where it will behave less well, which is one of the reasons why Riccardo is so careful about where he chose those priors to be. I'm not sure I have anything else to add at the moment, but curious to hear your thoughts, Carl.
Right. Well, I mean, my thoughts are very similar to yours. I mean, this is a very impressive and technically erudite piece of work, in particular, sort of showcasing the possibilities for computational phenotyping, and in the future directions part, one can now see some translational potential for this. So if this was sold as a validation of computational phenotyping using this, generic and very useful paradigm, very well studied paradigm, particularly apt for, say, attention deficit hyperactivity disorders or related disorders in neurology and psychiatry. I think this is a not only a conceptually intriguing piece of work, but one can see immediately the pragmatic applications for it. So that should be sold as much as possible. So most of my comments really are making the. Has it been written up yet? Have you written it up yet?
No, well, I'd like to write, and right now I've written the methods section, and I've started to write the results section of the paper, but we are still in a starting part of the work.
Right, good. Well, I mean, yeah, good in the sense that the feedback we can give is what bits need to be said very loudly and very clearly. What is important to clarify as you tell the story, as you motivate the design and the analysis. Just addressing the natural questions that readers and reviewers will have. And you've already encountered one, which was my first question: how on earth did you induce relaxed versus effortful? What you could call an instructional set or an intentional set. So choose how you define the thing that you're manipulating experimentally. And listening to your answer, I imagine you just used straightforward task instructions. Please provide a speeded but accurate response, or don't worry, relax about this. No one's going to record the results. Something like that, those lines. But in the write-up, actually put what you said to the subjects in the text, and then there's no ambiguity. And my recommendation, if you haven't already done it, is to just to again address Riddy's point that the implicit cognitive effort is exactly the functionalist target of the Stroop paradigm. So one way to sort of say, well, we are actually going beyond the conventional Stroop paradigm, and we're now making a distinction between implicit effort and explicit effort, in the sense that the explicit effort has this volitional aspect to it. So just to help the reader understand the extra factor, the third factor in the experimental design, is not that which is naturally induced by the main effect of, or the simple main effect of congruency. So I think that'll be easier for the reader to understand, and you can, you know, unpack or rename explicit effort, you know, as many times as you want, but make it clear it is not the implicit effort that is basically the foundation of the Stroop design. The other thing I thought was, when you're writing this up, I think there well, so again, I repeat, the sophistication of the analyses was very impressive. I mean, you have basically covered lots of issues in terms of meta-Bayesian analysis, and, you know, observing the observer and distinguishing between the subjective generative model, which is your active inference model, and the objective or experimenter's generative model that maps from belief states in the subjective model to objective measurements. Some of the objective measurements are easy, like choices, but others are less so, like the distributions of the reaction times. So sort of recommendations of feedback here. You spent a long time motivating the observation or objective model of the distribution of reaction times. And one useful way of motivating why you use the entropy of posterior beliefs over, I think it was actions. You had U as opposed to policies, but I presume that these were very shallow policies, so U and pi were effectively the same thing. One way to motivate that is, yeah, you got H as a function of C and E, but technically it was just the entropy of the expected the posterior over U in a later slide. Is that, if I remember correctly, you had entropy is equal to U transpose times log U.
Yes, but U is dependent on C and D.
Exactly, which is another point I'll make in a second. I think I'd make that explicit. I'd say that just let the reader understand intuitively how you're modeling the reaction time, and basically you are going to be saying something like, we're assuming that subjects or are modeling the reaction time as a lawful function of the uncertainty or inverse confidence about their decisions.
Okay.
Operationally, this is the entropy of the belief distribution, the posterior belief distribution over the next action, that itself then depends upon all the constituents that underwrite that distribution, including E, the habitual priors, and G, those priors that reflect the planning as inference, namely the expected free energy. Note that because the expected free energy depends upon prior preferences or constraints C, that this entropy depends sensitively on both the habitual preferences and the habitual priors over decisions or choices, and the prior preferences over the outcomes. Well, what I wanted to say was something along the following lines, that the generative model, when deployed to generate behavior, can be regarded as producing probability distributions over choices and actions that correspond to an idealized subject, given that subject's prior beliefs when examined an infinite number of times, or an idealized subject averaged over an infinite number of subjects, which means that if we want to use the responsive of this idealized subject to predict subject-specific behavior, we can only really predict the average behavior or the response of this canonical ideal subject, which means that we can only, although we can predict the average behavior of any given empirical subject, we can't predict the variability in that behavior unless we make additional assumptions. And one way of doing that is to make the simplifying assumption that the variability in this and that depends upon the uncertainty of the canonical or idealized subjects' beliefs about, say, behavior. And for example, and then you can describe how you've modeled the reaction time. You probably don't need to spend too much time on that, because all you can say is we created effectively a generative model of the sufficient statistics of responses, for example, the mean and variance, or the median and the variance. We did that by associating the mean with the average or the mean of the output of the generative model, and the variance we associated with the uncertainty or the inverse precision of beliefs about. So you can't do it any other way with this kind of setup. You can't model an individual trial. Well, you could, but it would take a long time to invert. It would be very different to invert the model. So I think it'd be simpler than just spending a long time talking about the distributions things. Just say we fitted the sufficient statistics of behavioral responses, where the sufficient statistics, for example, the mean and the variance, were generated from the model in the following way, and then just list down your how you computed the mean and the variance, and then you fitted the sufficient statistics of the behavior to those predicted. Thomas, is that quite right? How did you, in the fitting, in the variational Laplacian fitting, were you predicting the for example, the parameters that map from the entropy to the variance of the reaction times?
No, it was directly to the reaction times themselves. So it actually was fitting each response in the trial. So it wasn't just summary statistics or parameters of the overall distribution. So what Riccardo was describing in terms of finding these the alpha parameters and other parameters here. So that let me get this right. So the variance of reaction times here, that is actually just the variance that goes into the likelihood model for predicting each reaction time. So it's effectively like the kind of shaky hand parameter that we sometimes talk about, but in the context of reaction time.
I see. So the data that you were fitting were actually just a list of reaction times and choices.
Correct.
Right. Okay. That must have taken an awfully long time.
Yes.
I mean, we're talking days, if not weeks. Yeah. How long did it take?
Well, I have a quite good computer, so only like 2-3 hours per subject.
Right. Okay.
So I ran the code on Friday, and on Monday I had the result.
Right. Excellent. Okay. Yeah, I, this is a rather technical issue which you should keep away from the reviewers and readers, because that'll just frighten them or confuse them. But just for your for future studies, you might think about lumping together by taking averages of each individual's behavior and fitting the sufficient statistics directly, simply because it requires less inversions of the subjective active inference model, to do that.
Well, one of the reasons, Carl, for trying to take a little bit more granularity in this was that there are a lot of sequence effects in the Stroop task that often aren't captured in those statistics. And so the idea was to actually potentially account for those as well. So one of the things we found in the theoretical model was the idea that you're more likely to make an error if the in an incongruent condition if the previous stimulus was congruent. So if you asked green and green, or green text written in green font,
I see.
Then you're more, and the argument for it back then was that that seeing green font, or seeing the combination of green font, green text, and me saying green could be evidence for either the policy of naming the colour or the colour of reading the word, and therefore there's more uncertainty at the next time step in terms of which policy you select, and you're more likely to make an error by going the other way. And so by modelling sort of each choice in the task, that sort of captures some of those sequence effects. Hard to say at the moment actually how significant those were in terms of the final parameter estimates, but in principle they are informed by not just the overall summaries, but actually the sequences and which response is given after which.
Right. Okay, that's a very good point. And clearly, if you've got any transition dynamics with any precision, you will have ordinal or sequence effects in the data. Just practically, again, this is more for Thomas advising Riccardo or somebody else doing this kind of thing. The practical trick is to try and summarize each kind of task condition in just one running of the active inference scheme, and then match and then use that to evaluate the likelihood of some data, where you can summarize the data in terms of, for this condition, the average of this or the average of that, or some sufficient statistics of the distribution of the responses for that condition. In that instance, what one might do is have pairs of conditions, so that you're now accounting for sort of first order sequence or time effects. So you'll still have quite a lot, but you'll have the square, or something like the square of the number of conditions to do, but it'll still be less than doing every trial by itself. And this is purely for numerical convenience, is to avoid having to wait until Monday morning to see the results. It's just to try and compress down, to take the pressure off when inverting these meta-Bayesian models or objective models, noting that every step of the variation inversion involves a full inversion of the active inference model. So you want to keep the pressure down as much as possible in the number of times that you do that. But don't confuse the reader with this. Just try and either ignore it or put it in a footnote. Otherwise, that would be a distraction. But implicit, just out of for my interest. So, did you use the MATLAB SPM variational Laplacian schemes for the inversion?
Yes.
Yeah. It will be interesting in the fullness of time to see if you can replicate, and this will require taking the code that you've used and rewriting it in PyMDP. It'd be very interesting to see if you can replicate this the full analysis, the full phenotyping with PyMDP, and in particular, really the JAX version that's deliberately been designed exactly to solve this problem in seconds as opposed to weeks.
Yeah, like I got my results at the end of the day and I had like 80 participants in mine. So yeah.
Did you use the JAX version or the
Mhm.
no, is that the one that's not publicly available, or is it which one's the
Yeah,
one?
it's not publicly available only because the A learning, B learning has some errors in that, and that's exactly what I'm working on nowadays. But if this task doesn't require A learning or B learning, so it should be completely fine. But the branch is online anyway, so it's released in terms of it's there for the public to use, but you'll have to use a specific branch on the repository, not the main one.
Right. So Riccardo, just in terms of democratizing and making this a natural kind of data analysis, so you don't have to wait over the weekend for the results. It may be that you would want to do a comparative analysis using the gold standard MATLAB full variational Laplace scheme with the numerical gradients, and see if you can reproduce that, nearly in Python using PyMDP with the JAX branch, the automatic differentiation branch in it. And if you can, that would be good, because that's probably what people will actually be using in practice. And certainly if you start now to deploy this in a computational psychiatric setting, you'll probably want to be using that. You need to get these. You don't want to have to wait for a week to do all your or a few days to do a single analysis, especially when it comes to trying out other models and doing Bayesian model comparison. When you can't do Bayesian model reduction, you want the latitude to quickly ingest these data and evaluate the evidence for various models. And that's very practical. You may or may not want to mention that in a technical limitations of this approach. One is the computational cost of doing this kind of phenotyping, which is notoriously difficult because you've got to invert a generative model of a generative model, and that sort of added layer of complexity really does put a burden on the requisite inference schemes. But you can say people are deliberately trying to make this as efficient computationally as possible, and then possibly advertise the JAX version of PyMDP. But it will require you validating the PyMDP implementation, which hasn't got all the bells and whistles that the MATLAB implementation has. That will require a little bit of work. Can I just come back to the sort of comments on this particular paper? The interesting thing is that entropy measure, that U transpose log U, is exactly what is now used to evaluate the because under the simplifying assumption that no, that's right. No, in fact, if you go to the current code, then that corresponds to the expected log of capital E plus G, which is your log posterior, which means that you can interpret that in a way that's very similar to the interpretation of dopamine as scoring the confidence in what you're going to do next. So you can go right back to the original work with Philippe Schwartenbeck and colleagues, where it was noted that the precision parameter on the expected free energy seemed to behave when it is actually estimated in a way that very closely resembled the phasic responses of dopamine in the literature, and that hypothesis was also experimentally verified using fMRI, in the sense that VTA regions in fMRI were predicted by the estimated precision, which is, I think, your which one is it? No, sorry, it would be the entropy. Which means that you can say heuristically in previous interpretations of the belief updating specifically over policies, the precision or the entropy of beliefs over what I'm going to do next has been associated with phasic dopamine. So that when you're very confident about what's going to happen next, say I've just got a very, a conditioned stimulus that tells me I'm going to now secure my reward, you get a burst of dopamine because your entropy is very, very low. Whereas if you don't know what's going to happen next, or there is something that there's an omitted reward, so that now your confidence or your certainty about what to do after the omitted reward is extremely high, then you get a reduction in dopamine, or a reduction in phasic dopamine. So I thought that was a nice intuition, because that just is your H open bracket C comma E close brackets, which is just the expected free energy. So sorry, it's the expected free energy plus your habitual log priors. So it's E plus G, and they are the log posteriors. So there's a nice sort of three-way mathematical, physiological, and if you like, psychological link in terms of confidence about what I'm going to do. The neuromodulating mediation of that, which is more than likely to be dopamine, and the maths of this, that it is just the average expected free energy plus your habitual prior over that expected free energy, or over the policies. And then you can say, as we were saying before, this quantity is very much dependent upon C and E, and obviously E in the usual way. The other thing I thought that in the presentation you skipped over, which I don't think you should do in the write-up, is the actual model itself. And it would be, of course, lovely just to be able to refer to Parr et al. And say for further details, see that. But I think that misses an opportunity which you're bringing to the table, which is in a formal way to actually get into the anatomy of belief updating in a truly functionalist sense that underwrites this paradigm, and actually write out the calculus of this kind of belief updating and decision making under uncertainty and under different instructional sets. And I think if you just skip over that, people will just think it's a bit of magic, it's a bit of computational magic, whereas it's not really meant to be. It's meant to be a way of rigorously and formally defining both the neuronal message passing, but also the belief updating that underwrites our decisions under uncertainty and subsequent behavior, and to actually identify the targets of various priors that could explain abnormal behavior and or inter-subject variability. And as you've illustrated here, they will invariably affect the precision of something, whether it's actually directly through manipulating C or multiplying a base C or a base E by some number. It's 99.9% of the time it's always a prior belief about that's written in terms of confidence and precision. So to make that formally apparent, though, I think you need to have at least one figure that I'm sure Thomas will lend you his original graphics, with possibly a very long figure legend, just walking people through the structure of the generative model, which is not simple. But neither is a Stroop task. So I think people deserve to see the actual structure of the generative model, the subjective generative model, and more importantly, to actually see the functional form that underwrites the choices that people make, as expressed in terms of a linear mixture of E and G, to which you apply your sigmoid function, and then write out the E and G explicitly as functions of little e and little c. So that at least they don't have to be one equation, but at a glance, somebody like me, for example, can just see why it is the case that changing C, which is now a free objective parameter, so a free parameter of your sort of meta-Bayesian analysis, does indeed have a profound effect on choice behavior, because it increases the precision of your prior preferences, which in turn increases the precision of your expected free energy, or the planning component of your belief updating about what you're going to do next, which means you've now got more confident behavior, but it's also more constrained by your prior preferences. And so to be able to see that and then say what we are doing is we are calling this motivation. And we can call it motivation because, and then you can express that in terms of cognitive effort, in relation to the original conceptual target of Paretel. Thomas, does that sound sensible? Because otherwise, I think it's I know that you put a load of work into the phenotyping part, but the whole point of doing this is to have, I repeat, a formal, rigorous anatomy of beliefs and decisions that can be related both in terms of its functional form parametrically, but also ultimately in terms of the underlying neuronal process theories and message passing.
Yes, I think what you say makes a lot of sense. I'm often a little uncertain as to where I stand on the sort of tension between providing a sort of relatively complete unpacking of the previous work and how much of that is necessary for the understanding of the phenotyping, and sort of the price you pay in terms of the length of the paper, the sort of restriction in where you can then submit and those sorts of things. So I definitely agree that having a figure that deals with the structure of that generative model and that it is explained makes sense. I also very much agree with the idea of having an equation that makes a clear link between the parameters and the decision making itself, so the policy selection. Just as a side note, one nuance I'd add into that is that yes, the entropy of my actions as opposed to my policies will match that of my policies in many cases, but actually one of the interesting dissociations here is that in the context of a congruent stimulus, it won't. And the reason it won't in a congruent stimulus is that either the policy read the word or name the color will predict exactly the same action, which is in fact one of the reasons why you get this different set of this different distribution in each of those different conditions. So I can be much more confident, despite the fact that that my policy, or even if my policy is completely uncertain. But in general, yes, you're right, that there will be that link, and it makes a lot of sense to highlight that link in an equation showing at least the uncertainty of the policy and how that depends upon these different parameters. But yes, I think it's there's a difficult tension as to sort of brushing over it to the extent that nobody has any idea what's going on, and as you say, it seems like magic. And then on the other side, sort of over-explaining it, and there's also a trap in the middle, isn't there, of sort of giving a little bit of the information that frustrates people without actually giving them enough to grasp.
Yeah, well, one thing which both you and I have just alluded to is not to burden the main text, but to have a really long figure legend. So I find that's the best compromise. So people can speed read the figure legend if they just get a little bit overwhelmed with the mental contours of understanding these generative models, or if they're fluent in specifying these Markov decision processes, that they can find all the necessary details, or at least references to the details, to build an intuition as to how it worked. So I wasn't suggesting you spend page after page describing active inference, but I do think a couple of graphics, one of them equipped with a 500-word figure legend, just for those people who want to push through the magic and actually understand what's going on here, would be useful. I mean, just for example, I was personally recall and got up on screen the original paper just to remind myself what was going on. To understand and appreciate what was happening. And a lot of people, I think, would want to be able to do that. But if you can just provide them with that material in one page, with big figure, long figure legend, I think that would be quite sufficient.
Would you focus predominantly on the specifics of the generative model, or for those who are less familiar with that, would you focus on the belief updating process itself? I think that's
Well,
the other
I think you just structure the generative model in terms of the factorization and the hierarchical depth. Do not worry about sort of vanilla belief updating and variation-free energy, but do really drill down on the expected free energy and the contributions to your beliefs about your decision. I think that's where that's where the interesting bit is, and of course, you don't need to worry about active inference in terms of variational free energy, but I think you do need to sort of communicate the complexity and the structure of the generative model, and in particular, how you're understanding the Stroop paradigm as putting in opposition habitual responses and beliefs about the kind of responses I commit to, versus those that are very context specific and require some deliberative planning. So how would we model that formally under some generic or universal belief updating scheme? Well, in active inference, that's quite trivial. We just need to specify prior beliefs. This is the kind of thing I normally do, that I've learned, that has been automated and experience dependent, namely E for experience dependent, and contrast that with the deliberative part that depends upon the goodness of a policy in this particular context. And we denote that with G, which stands in for expected free energy. And then say, well, what makes a policy good? Well, then we've got the epistemic and the pragmatic, or so I think people should be taken by the hand to see how these sort of narrative psychological constructs, cognitive constructs, actually can be naturalized mathematically, or in terms of at least sort of probabilistic programming or belief updating. But so you don't need to worry about inference, and but I do think it's important that the sort of the trade-off between the priors and the expected free energy, and what contributes to the expected free energy, that I think that is important.
Okay.
Can I just ask one final question? In relation to the PEB analysis of the between subject effects, one thing which one always has to bear in mind, and to a certain extent you sort of pointed to explicitly in terms of the yin-yang between C and E over subjects, was the conditional dependencies between the estimators of C and E given the empirical data. So if these things are positively correlated, then they can appear as very sort of negatively correlated in terms of the if you just look at the map estimates. Whereas if you look at the full covariance structure, you can see immediately that you're just measuring one thing effectively, and sometimes it appears as a high one of those or a low one of those. So was the PEB analysis, did you take up the posterior correlations between C and E into the PEB analysis?
Well, yes, I think so.
Excellent. Well,
I need to check, but I think so.
In fact, if you use the SPM code, you must have done, because it expects fields that are the posterior means and correlations. So I think it's important to mention that for reviewers. This is more important than some of the other things that you might think reviewers will get upset about, but accounting for conditional dependencies in the implicit hierarchical or random effects modeling that is afforded by parametric empirical Bayes is an important aspect. So, you could even say that when you're just looking at the maximum posterior estimates over different subjects of E and C clearly that there's no information about the posterior correlations or covariance between the two, and therefore you can either have a very high C or you can have a big difference in C's or a big difference in E's, and that looks to be like a really interesting source of variability, but it might not be if the posterior correlations between C and E are intense because they both produce the same kind of data. So it might be worthwhile to say, please do not overinterpret the variations over subjects in E relative to C, because there could be posterior correlations, because these estimators came from the same data set per subject. However, we can accommodate these posterior dependencies by using parametric empirical Bayes or a Bayesian random effects analysis. We therefore submitted the posterior expectations and covariances to parametric empirical Bayes under a Bayesian regression or linear regression model at the between subject level, and then report the group estimates. Moreover, then we're particularly interested in sort of testing various hypotheses about, was it just motivation, was it just bias, was it a mixture of both? Please see below.
Okay.
Wonderful. Thank you, Carl.
It was wonderful. I've run out of things to say other than admiration.
Definitely. Are there any other questions from anybody else? Or Riccardo, if you have any other questions?
The other thing that I want to ask is if you to ask to Carl, but to all the audience, if you think that the use of alpha and V only for the reaction time model is a sensible thing, because I defined these two values that are different for each subject, and I consider them fixed in the main model, and I consider them in the main model in order to make the model account only for the differences across conditions. So my question is, for you, it's a sensible thing or not?
If you're asking me, that's an empirical question that you would test, because if I remember correctly, the alphas and the V's are part of the objective likelihood model mapping from the probabilistic outputs of the active inference model, and as such, they are explaining empirical data. So if it is the case that different subjects effectively have a different mapping, then you should certainly model subject-specific values for these. On the other hand, if it is the case that these values are conserved over subjects, plus or minus some random effects or fixed effects, then you'll get a simpler model and a better model in principle if you don't include them. One way operationally to so that's in the fitting and the pen. Yeah, in the fitting themselves, operationally, the distinction between a random effect and a fixed effect is usually obtains when you enter certain parameters into your parametric empirical Bayesian model. So if you have fitted separate alphas and V's to every subject, and you have not put those into the PEB scheme, which I don't think you have because you've just put C and E into the PEB scheme, one way of explaining that to the reader, or indeed yourself, is to say that the alpha and V and everything else that does not include C and E were treated as fixed effects. This is in contrast to the handling of C and E as random effects, what do we mean by random effects? Well, we mean that the subject-specific values of the C and E could be generated from a group mean, and then one adds a random subject-specific effect to give the subject-specific value. So the meaning of a random effects analysis is that you are assuming that certain subject-specific parameters can be generated from sampling from a common distribution and then adding a subject-specific random effect to it. And what that does, it puts certain constraints on some parameters. So almost paradoxically, the random effects are more constrained because you think you sample these from a common underlying distribution. Whereas the fixed effects can do what they want. So effectively what you've done is you've treated your alphas and Vs as fixed effects and your Cs and Es as random effects. I think that's a proper way to do it. You might get more efficient inference about Cs and Es if every subject had the same alpha and V. But it's a gamble. So, and it doesn't, you could try it both ways and see if you get better inference about the random effects. If you've got good results, which you do have, then I wouldn't bother. I'd just say we treated all the parameters. We estimated subject-specific, or we evaluated posteriors over all the parameters on a per-subject basis, and then we treated the parameters of interest, namely bias and motivation, open brackets, E and C, close brackets, as random effects. In other words, we assumed that there was some underlying population mean from which these parameters were sampled and then equipped with a random Gaussian variate in order to produce the particular estimates that we observed. I think that will be fine. The short answer, I can't answer that question. You have to use the data to answer that question. And it really does depend upon whether in real life, metaphysically, each subject had a constant alpha or V or not.
Yes, because at the beginning, I used a default value of alpha that was 0.5. That was also the same in your paper with Thomas. But I had in my data set some subjects that are very fast and other subjects that were very slow. So I had to put something in the model because it was accounting for how the participants were fast on average. And
yes.
I wanted to model the differences across conditions.
Yeah, I think that's perfectly fine. And the fact you're using e to the power, I'm sorry, just thinking that also means that you're talking about proportional differences. And if you want to say that, we were not interested in the average speed. We were interested in condition-specific differences in the speed, as modeled by condition-specific differences in the entropy or confidence about subsequent actions or outcomes.
Okay, thank you.
Hi. Yep, Giuseppe. I can't hear you. Can anybody else?
No, he looks happy.
Yeah, no,
in a
can't
quiet
hear
sort
you.
of way.
Oh, no.
Oh yes,
Now we can
that
hear
works.
you.
Okay. Well, thank you very much, Riccardo. Thank you, Thomas. Thank you for all the work with Riccardo, and thank you, Carl, for all this valuable input. And thank you, Ridley, for hosting the session. I was wondering about your discussion on this entropy measure that reflects the precision of the posterior distribution of our policy of the choice. Do you think just that measure could be something that could be tested for differences across, let's say, people with different polymorphism of the dopamine receptors, for instance? Using, of course, this this task?
I'm not sure about polymorphisms, but I'll ask Thomas to comment upon that as a neurologist.
Because if I mean, the rationale would be that if that reflects the precision of the policies, basically and so the confidence with which you're selecting one policy over others.
Yeah, no, absolutely. No, I think that's an excellent idea, but the polymorphism bit caught me. If you'd said people with pre-symptomatic Parkinson's disease or following an LTP challenge, an L-tryptophan challenge, or something along those lines, where you're actually changing dopaminergic discharges.
Right.
Yes, yeah, absolutely. The polymorphism bit caught me because I don't know what that means basically. Thomas, what does that mean?
I mean, I suppose it's hard to know until we know if there's a behavioural variation that you see with the polymorphisms. So one could imagine that with different polymorphisms, you have different degrees of function of dopamine receptors, and whether that produces enough behavioural variation that you can start to fit these, I think is something you wouldn't really know until doing it.
Right.
Do you know, Giuseppe, if there's any data suggesting that polymorphisms of this sort of effect on other measures in the Stroop task?
No, I'll have to look.
That would probably be the first step in terms of answering that one.
Just because we were discussing with Thomas about this. I mean, of course, a pharmacological challenge with levodopa or things would be, but of course that would be much more difficult for for ethical reasons, or it would be for the ethical committee would be something much more difficult. And another thing I want to ask, maybe to Ricky, which seems to be involved in the PYMDP. When I checked, it seemed to me that you could not yet use it for doing for building deep models. Can you do it now? Is it? Can you build like deep modeling in PYMDP now? I mean, like the one
Riddy can hear us. Riddy, can you hear us?
I can.
Oh, right.
Okay.
Sorry, can you say that again?
Yeah.
Like lagging a little bit.
Yeah. So the last time I checked with the PYMDP, it was not possible, at least not in a straightforward manner, to build deep models, with the...
Oh, so you're asking whether that's possible within
Right.
JAX, or sorry, I thought you were asking Riccardo whether he can turn it into a deep model, not addressed to me, but yeah. Not in the library as a specific argument that you can just turn on or turn off, but it would require a little bit more extra coding from your end. But even in JAX, it would be the same thing in JAX. There's no particular function or argument that has been created to do that.
I see.
But you can scale up using JAX multiple agents. So they can all have the same generative model and the same generative process, even different generative models, but scaling it up, and run them all in parallel. And that's basically the thing that allows it to be more computationally efficient. But you could like just edit the agent function in itself and add the deeper model in there, so then you can do model fitting with the deep hierarchical model in there. Yeah, but it's not easy.
I see. And and I also appreciate Carl's suggestions to be clear in the paper about the difference between the type of effort, which is basically, I mean, Kahneman's idea of the amount of cognitive resources that are exogenously, commanded by the task difficulty, and that kind of voluntary or self-control effort that we actually wanted to investigate. So these are two different meanings of the same word. There is actually a third one, which is the affective quality of effort. That kind of usually aversive, although sometimes may not be aversive, but that quality that is associated with putting effort in a task. So yeah, but I think it's a very good suggestion to be clear about these two, at least these two levels of effort, or the implicit and explicit, or the voluntary and the one that is just mandated by the difficulty of the task.
Thomas, do you want to comment upon the phenomenology of effort and its metacognitive?
No. I partly say that so I've been seeing patients all night, so I'm very sleepy.
Oh, I see. Sorry.
The effort it would take me to sort of come up with something coherent, I think, would be too much investigation.
I think at this stage, then, is it, if one wanted to move into that sort of affective aspects and phenomenology, then I think you've got the right foundations here by having these sort of precision controls at the deepest level. I think, and then if you were Lars Stanford Smith, you'd say, well, I have another level now that's predicting that level, and then you'd have the affective and sort of self-referential sort of metacognitive aspect that could be declared. It could be declarative and explicit in its way. So I think you're moving in the right direction. Whether somebody like Lars would say it has a phenomenology yet, I think you probably need another level before sort of actually doing that bit, the affective part of it. Unless you're Mark Stones, in which case it's all feelings, it's all precision.
That's right. Okay.
All right. Wonderful. I think this kind of marks the end of it, unless anybody else has any other questions that they'd like to ask. Otherwise, I'd like to thank everyone for asking the really great questions and giving some really helpful feedback to Riccardo. I'm sure it'll all be very helpful, and I'm excited to read the paper. So yeah, thank you all. Can we please just all unmute and have a final round of applause, please? Thank you for Riccardo and for us all. Thank you so much. Yeah, see you all either tomorrow or next week.
Thanks.
Bye.
Thank you.
Thank you. Bye-bye.